To introduce you towards Dr. Sami Shende. Sami Shende serves as the director of the Performance Research Laboratory at the University of Oregon and the president and director at Paratools. He is the founder and lead developer of the TAU performance system and the program database toolkit. He has designed the instrumentation and measurement layers of TAU and is responsible for releasing TAU and incorporating new feature requests. This includes source analysis toolkits, binary rewriting tools, and wrapper interposition libraries. He also serves as the PI and co-PI on several grants for the development and application of TAU. He has contributed and designed the HPC Linux OS distribution available for download from the Paratools website. His research interests include instrumentation, measurement, and performance analysis tools for HPC, compiler optimizations, runtime systems, and also operating systems. So requesting you to give a round applause to Dr. Sami Shende, and the session is over to you, sir.
Thank you very much. Thank you for inviting me today. And I would like to thank Ganesan for all his help. I have put the slides in the chat window. I hope you can all access them. And today's talk will focus on exascale computing, the extreme scale scientific software stack, and the Tau performance system. So there are two challenges that I would like to cover in today's talk. The first is that with growing hardware complexity, it's now getting harder and harder to accurately measure and optimize the performance of our HPC and AI ML workloads. The second challenge that we are facing is that our software is getting really complex. It's now getting harder to install tools and libraries correctly in an integrated and interoperable software stack. And to address these two issues, our research will show the Tau performance system that aims to deliver a scalable, portable performance evaluation toolkit for HPC and AI workloads, and the extreme scale scientific software stack, which aims to deliver a modular, interoperable, and a deployable software stack across architectures. And it aims to lower the barriers of the use of HPC and AI ML technologies, and also enable uniform APIs where possible. And these are the two websites where you can find out more information about the two projects I'm going to discuss today. So the Tau performance system aims to support all the HPC platforms, compilers, and runtime systems, and provide portable instrumentation, measurement, and analysis capabilities. By instrumentation, I mean adding hooks to your code, probes that will trigger the measurement routines. And this can be done at the source level, at the linking level, even at the executable level. And once those probes or hooks are there in your code, when you run it, it can generate profile files or traces. And you can then analyze the data using tools from Tau, such as Paraprof, Perf Explorer, or third-party trace analyzers, such as Vampire from TU Dresden in Germany, or JumpShot, which ships with Tau. So you can do automatic instrumentation of a number of different languages. This includes Python, which is critical for many of the AI ML applications, C++, C, Fortran, even UPC, Java, Chapel, and other languages. We have support for instrumentation at the runtime layer, and we support MPI, the message passing interface that is ubiquitous across nodes for programming. And OpenSHMEM, RMC, even pthread, OpenMP, and other GPU runtimes, such as ROCm, CUDA, OpenCL, OpenACC. And then once you generate the data that you can visualize using Paraprof, and even store it in a database called TauDB. We also have a 3D profile browser integrated in Paraprof. So you're probably wondering, what can Tau show me? How can it help me? Well, you can use Tau for the performance engineering of your applications. It can show you how much time is being spent in different code regions. At the application level, at the outer loop level, even within the loops, you can see the contribution of each statement, the time spent in OpenMP loops, in kernels running on GPUs, the data transfer between the host and the device. Instead of time, you could use hardware performance counters from tools such as PAPI that can show you floating point instructions, level 1, level 2 data cache misses at the level of statements or loops in your code. You can see the memory usage of your code, where it gets allocated, deallocated, even the memory footprint. And what do I mean by the memory footprint? You see, once your program is loaded into the memory, it has the stack, it has the heap, it has the data, the text, the BSS, uninitialized data, the complete memory usage of your program, and what is the max value from start to finish. You can see the high water mark of the memory usage. You can track the memory footprint. You can see the energy usage. You can even see I/O. Like, show me all the files that my application accessed. How much data was transferred in each POSIX I/O call or MPI I/O call? What is the peak read and write bandwidth of individual calls? What is the total volume? How does the application scale? What is the runtime breakdown of your code across different core counts? You can do that using the TauDB database and Perf Explorer. So the first step in using a tool, in fact, any performance evaluation tool, is to add the hooks into your code. While this can be done at the source level using Tau shell scripts, using the program database toolkit for static analysis of C and C++ codes, you can also use the compiler. The compiler can emit hooks at the routine boundaries. And then you can tell it what to instrument or not instrument using a selective instrumentation or a filter file, so you can reduce the runtime overhead. But there's an even better solution where you can just launch the uninstrumented binary. Yes, with no changes to your source or the build system, using a tool called Tau Exec. This works for dynamic executables, which is what we all use. And you can just launch it with the Tau Exec tool, and it will then use the LD preload mechanism and preload the Tau dynamic shared object and intercept the runtime calls, and then you can make measurements. When you make the measurements, you can generate profile files or traces. Profiles show you how much total time was spent in each code region. So if there's a function that's instrumented and it gets called 100 times, then at the end of the execution, you'll get a single line of performance data which says this function was called 100 times and it spent 50 seconds of inclusive or exclusive time in it. Now, tracing, on the other hand, can show you where the events take place along a timeline. So you can see what each process is doing, where it sends the messages along a timeline. Profiling also uses sampling or direct instrumentation. With sampling, you can periodically interrupt the program and then see where the program is, the program counter, associated with the source line number, and then based on the number of samples collected and the total time between the samples, you can then create an estimate of where the profile shows where the time is being spent. Now, the Tau Exec tool that I mentioned allows you to operate on uninstrumented binaries. It can then load wrapper libraries. It can instrument or add hooks at the MPI level, at the OpenMP level, at the IO level. You can track memory calls. You can even wrap external packages, and then you can enable all the features of Tau, such as generate a communication matrix display, enable event-based sampling, or generate traces in the OTF2 open trace format. Here is a quick start guide. If you have an uninstrumented code, you want to run it with Tau, you can just say Tau exec-EBS or event-based sampling and then run it like this. With OpenMP, we have support for OpenMP tools interface. You can specify tags of Tau's configuration. You can use pthread. You can even use a tool called Tau_Python to insert hooks at the Python level along with event-based sampling. If you have support for GPUs, you can enable the kubT options with Python or specify serial if it's not an MPI program. You must say -t serial. And then launch pprof or paraprof to view the performance data. If you want to generate trace files, you enable options. Now, this is how Tau works. You can enable some environment variables like Tau trace and then set Tau trace format and then launch the Tau exec tool to generate the trace files. We can also use Chrome and Perfetto trace browser like this. So what do you see when you launch paraprof? You see all the MPI ranks, and for each rank, you see the color-coded functions that are kind of packed together. And you can then turn off the stack bars together. So each function has its own space. You can see, for example, if you hover over the MPI weight, this blue color, it says that it's MPI weight, it's exclusive, inclusive time, and how many times it was called. So note, this is the total contribution of MPI weight across 16,884 calls. You can look at the thread statistics table. Here is how I can launch a Python execution with enabling support for CUDA profiling tools interface or kubT, enabling event-based sampling. And instead of Python, exifel.py, I can say Tau Python with these options and then run the unmodified Python binary. And then I can observe the GPU execution. I can see the kernels executing on the GPU, how long they take, and even the memory to device, memory host to device transfers. This is the thread statistics table where I can expand, and then I can see where the samples were collected. This is on an IBM system. This is at the Oak Ridge National Labs, and it's the large Summit system at Oak Ridge, and you can see the exact location of the code and even the CUDA host to device and device to host copies and the Python functions with MPI. Now you can look at a profile and then launch paraprof. You can sort it by clicking on these columns. Here I can expand this. I see here that the application took 9.3 seconds total, inclusive time. And inclusive is from start to finish of that function, a top level function called .tau application. Exclusively, it took 9.1 out of the 9.3 seconds. And with sampling, I can explain 9.01 out of the 9.1. This is close enough. And I can expand and see where the samples were collected and even go down to the source level and see exactly which line in the code, like line 228 in this solve subs.f function, in this binv crhs underscore function took so much time. This is the context event window that can show you the IO operations and what is the total IO bytes transferred. You can even track inside a system level library. Like this is the Spectrum MPI from IBM, and I can see within MPI BCAS exactly what it was doing. This is very interesting. All you have to do is launch it with Tau exec, and you can see what's happening. You can even unwind the call stack where you get an event and then see exactly what each function was doing. Here is the example of the Candle project, which is a deep learning and framework from Argonne and ECP. And you can see exactly which eigenfunction and which kernel was executing for how long. You can also see it across different threads. So you can see the exact location and you can demangle all the C++ function names. Or if you have a solver and you just launch it with tau exec-ebs, an uninstrumented code, you can see exactly how much time this line of code was taking in a point solver across different MPI ranks. Now, if you have a function like MPI receive, and you want to see exactly which instance of that was taking how long, you can turn on call site profiling. With call sites, I can then partition the total time in MPI receive, which is like 14.6 seconds across this line of code at line 68 in this exchange1.f. It took 12.6 seconds. And then at this line 86, it took 2 seconds. So you can partition the time in any function using call site instrumentation. You can see the bandwidth of operations, read and write, when you launch it with tau exec with IO profiling. You can even observe it in a 3D profile browser. Now, this is a very interesting profile browser, and maybe it may be interesting to show you how this works. So I have a paraprof demo.ppk, and let me just make it bigger. And here is the paraprof browser. I can now click here and see exactly how much time was spent in this loop. I can go to the windows. I can look at the options, stack bars together, and then there are many threads of execution. But instead of looking at thread statistics table and seeing exactly the time spent on each function in a text display, I can see a 3D visualization. And here, what is interesting is I can see the shape of the execution. I can see, for instance, by clicking here, I can rotate the 3D view. Here I see all the functions along this axis. I can see the ranks along this axis, and the height shows you the exclusive time. In this particular case, I'm looking at function and threads, and I can even go to the exact line of code and see which CPU is taking how long. So, for instance, where these two lines intersect, I can see that on this particular function called loop aorsa 2D stix, it's taking 129.5 seconds. And you can see exactly what all these 500 and 256 CPUs are doing. You can see the half of the machine is doing this, the other half is doing that. These two functions are kind of inverse of each other. You can see a scatter plot where you see each rank is a ball, and then you can see the MPI barrier takes between 31 seconds to 260 seconds. There is this one CPU that does something different. In fact, it's simulating a nuclear tokamak reactor, and the CPU that gets a central axis in the cylinder has to do more work. So then you can see that's the difference in this particular case. So paraprof is a very intuitive tool to use. And you can see these axes where the two axes intersect. You can see the time spent in that function. You can see communication matrix displays. You can see exactly what each process is doing with jump shot, or even Chrome or perfetto.dev, where you can load trace files processed in this manner. This is the Vampire tool. It is showing you the time spent along a timeline display. It's the state of the art from trace visualization. It comes from TU Dresden in Germany. And you can then enable such detailed executions using the Tau's Cocos interface. Cocos is a library for expressing parallelism in your code using C++ Lambda functions. And then you cannot, you don't have to worry about which processor architecture to code towards. You can write the code using Cocos, describe the work to be performed, and then Cocos can map it to a GPU, whether it's Intel, AMD, NVIDIA, or P threads or OpenMP threads. So you can even specify your names of functions like this. So Tau supports many different runtime systems. We already heard about MPI. It supports the MPI tools interface as well as the MPI profiling interface. It supports pthreads, OpenMP, OpenACC, OpenCL, CUDA, level 0 from Intel with DPC++ and SYCL, even ROCm, Cocos, and Python. And the best part is you can mix and match them, whether it's MPI with OpenMP or Cocos with pthread with MPI or Python with CUDA and MPI. And this is how you launch a tool. You can say Tau exec with kubectl or OpenCL or OpenACC or other GPU runtimes. And you can enable IO profiling, OpenMP tools interface, even event-based sampling at the function, file, or line level. So with this introduction, I want to move on to the second part, which is the extreme scale scientific software stack. I mentioned that the tools are getting harder to install. And in the Exascale computing project, we have 3 different parts. There is the application teams, application development, software technology, where we have over 70 unique software products, and then the hardware integration, where we install all the software on and applications on the HPC systems. So our roadmap in the Department of Energy in the US is to build these large scale HPC systems. And you can see that we had systems such as the Summit from Oak Ridge Sierra at Lawrence Livermore, which includes the IBM systems with NVIDIA GPUs. And now we are going into the next phase where we have AMD, Intel, and NVIDIA GPUs for the Exascale systems. Our goal is to build a comprehensive, coherent software stack that enables application developers to be productive and to deliver high quality and robust software products. So we have many technical areas. Here are some. The software technology area includes programming models and runtimes, development tools, math libraries, data and visualization, even the NNSA ST area, and the software ecosystem. Among these areas, we have software development kits for all of these, and I serve as the PI for the programming models and runtimes area, which helps develop the E4S stack. Our goal is to develop this software stack and deliver it to the facilities, vendors, and all of you, so that you can be more productive. You can install the packages very easily, whether it is on bare metal or using containers. And we have quarterly releases. We just had a release in November. Last month, we had a 21.11 release. And you can find out more about it at the e4s.io webpage. So what is E4S? E4S, or the Extreme Scale Scientific Software Stack, is a curated SPAC-based software distribution. SPAC is a very versatile package manager. You may have used other package managers such as Yum or apt. SPAC allows you to build the packages from the source code and even has support for binary build caches for multiple architectures. Now we have E4S binary build caches for x86-64, PPC-64 LE, the IBM Power architecture, and the ARM64. We have containers on Docker Hub and our E4S website. And we also have a range of containers, which includes base images to all the way to full-featured containers with GPU support. We have recipes for creating your own custom images, and even support for GitLab and validation test suite, and a virtual box image that can help you understand how these container runtimes work with a number of these runtimes. We have AWS images and GCP images to use. But in case you're wondering, how do I use E4S with containers? Well, what are containers? Containers are a lightweight collection of executable software that encapsulates everything needed to run a single specific task. It does not include the operating system kernel, and it's based on Linux. So Docker is a very widely used container runtime. If you want to compare the runtimes, you can see that there are hypervisors, where a hypervisor is on top of the hardware and it has multiple operating systems with their own kernels. You can have a type 2 hypervisor where you have a hypervisor on top of an operating system running on hardware, and then you have virtual machines like this. But instead, if you look at containers, then you have a container running directly over the container runtime and accessing libraries and operating system, but the container does not have the kernel like these cases. So you're not running two different kernels, it's using the same kernel of the host machine. So that makes it very efficient. You can just nail down all the dependencies, all the moving parts in your packages, and create a reproducible artifact. You can have a single container that has all the software that can be used to reproduce your results. So we have many applications that rely on multiple products. And here are just some technologies that are used by 5 applications. There's the Exa Wind. It's a turbine wind plant efficiency CFD simulation software from the National Renewable Energies Laboratory. And the other applications such as subsurface, whole device modeling app for the ITER reactor, the Exascale, a cosmological code, and the Marble multiphysics code. And you can see what each of these packages need. So here are the 5 different applications, and you can see all the tools and libraries that they need from multiple SDKs. So we have SDKs that span all of these 6 or 7 areas, going from programming models and runtime to compilers to tools such as Tau. And Tau is included in the E4S distribution, along with other tools such as SuperLU, Trilinos, and visualization tools. You may have used some of these tools already. You may have used LLVM compilers. You may have used MPitch or OpenMPI. And we create these SDKs and then build and test them and then deploy it on the facilities. Here is the XSDK, or the math libraries, that has a whole range of packages, and these packages support GPUs. So building these packages with the right set of options to use, say, NVIDIA or AMD GPUs becomes a challenging task, and we make it simpler to use that. So the core questions we are addressing are: how can new ECP software capabilities be effectively and efficiently integrated and also sustained? How can E4S build upon, leverage, and extend existing capabilities and activities? How can it become a sustainable, open, collaborative software ecosystem for HPC? So starting with our first release in October 2018, we have released many versions. The latest version has 91 full release products. And it also includes, besides HPC, it includes AI ML packages such as PyTorch and TensorFlow. It has core design packages like Amrex, Kibana, MFEM. And we have several outreach activities. We have hands-on sessions, videos, and all of this is archived and stored on the E4S webpage. So you can just take the training at your own sweet pace and see the slides, see the videos, and learn more about E4S. This is the download page of e4s.io, the latest 21.11 release. And we have containers. Here is a GPU container image for PPC64LE, or the IBM power system. And we have support for x86, PPC64, and multiple architecture images, excuse me, and even base images. We have base images for NVIDIA GPUs, AMD GPUs, and Intel GPUs as well. And support, some of the packages support all 3 GPU runtimes like Tau. You can go to Docker Hub and access these. All you have to do is do a Docker pull like this, and then launch it in such a way. Here, you can see the list of the packages that are there for x86 64. And we also have GPU runtimes. So if you just download a single container, you can get the Intel One API, you can get ROCm from AMD and NVIDIA, CUDA and NVHPC compilers. This is for x86. You can see all these packages, including Tau and Trilinos. You can even see with SPAC, you can say, show me the dependency listing, verbose mode, Trilinos version 13.2.0 with CUDA, where CUDA architecture is 80. So you can see CUDA architecture is 80. You can see CUDA 11.4.2 was used, and this is using SPAC. There's a very good tutorial on SPAC package manager. I highly recommend it. And this is using the A100 GPU with the CUDA architecture. So you have this solver library already built for you and available in a binary form, which has so many other packages included in it. And all of these products are available on multiple operating systems. So you can see this is the listing for IBM Power 9, where we also support CUDA and NVHPC 21.9. And you can see the list of all these packages available pre-built for you. So you just have to download a Singularity container and launch it. You can also install it on your own using the manual installation instructions. Here are the instructions, and you can see how to use the build cache. And there are YAML files for SPAC. So you can install it for bare metal environments where you don't want to download the container. You can just install it directly, and even use the mirror where you can download the binary images of these packages. Here is an example of how we are building these packages with support for A100, where the CUDA arch flag is 80 over here. We have also built it with ROCm or One API. You can do a SPAC installation locally on bare metal with this YAML file, or you can create a Docker container yourself, such as this, and give it a name. It will pick it up from the Docker file, and you can get all that information from our web page. Now we also have a build cache, as I mentioned, so you can use SPAC and pull in the binaries. Pull in the binaries for IBM or x86 across different operating systems. And we have over 75,000 binaries in our build cache. And this is just the inventory page. We also have a monitoring framework for our jobs. Some of these are pull requests that are merged for SPAC, and you can see exactly where the jobs were executing on which University of Oregon or AWS system, and what kind of failures are reported for when a recipe for a package is not correct and it doesn't get accepted into the SPAC framework. You can see exactly what the errors were. So it's all very transparent. You can get all these images for multiple platforms from Docker Hub directly under the ECP E4S. And you can see who's downloading the Docker image, how many times a Docker image has been downloaded, starting with the base images, the GPU specific images, or the full image. For example, the base image for this Ubuntu package with SPAC in ECP is fairly popular. We have over 1 million downloads for that. And these are the multi-platform images that you can use for even GitLab runner tasks. They are separate images like this for the runners, which are bare bones. You can use those images for building other packages or just using them to create your own custom image. And we also have a doc portal where we can document what all the packages are, where they are. And instead of just hosting packages and writing static content, we actually go and rake their GitHub repos. And then you get the latest information. You can see when the application or the package was updated recently. You can see search for a particular package like mpage or OpenMPI. And then you can also see exactly what the README files or change logs or license files are. And we also have an image on AWS, which you can use. Here is the AMI. It has a large number of packages as well, pre-built with Tau in it. You can then look at the performance of the code. You can see reproducible Docker recipes. We have community policies if you want a package to be accepted in E4S, and you can learn more about it here. And here are some membership criteria. It should have a SPAC package. That's the first important thing, so that it's all based on SPAC. And I also have, we have developed a tool called E4S CL. It's a tool to launch MPI jobs in E4S containers. And you can replace the MPI in the application running in, say, Singularity or Shifter with the system MPI. So you can have faster inter-node communication. It just needs three things: what kind of backend it is, whether it's Singularity or Shifter, where is the image located, and what should it do when it launches the container. And you initialize this. Here is a startup script. For example, it says load the Tralinos package with CUDA, where the architecture is for A100 or 80. You just start up, load this and unload the MPI. And then you can initialize it like this, and then run your application with MPI run to use the system MPI in your path. This is the architecture of the E4S container launch tool. And here are some exercises. You should say on x86-64, you could just download the image like this, clone the test suite from GitHub, and run the code with Singularity. Go to the Tralinos directory, clean, compile, and run the code, exit. And if you wanted to use, say, a system MPI like, say, Intel MPI, you could do that with sourcing the Intel one API setvars.sh, and then follow it similarly, and then it will just replace the MPI and allow you to run it like this. So in summary, what is E4S? E4S is an extensible open architecture software ecosystem that accepts contributions from around the world. It's a framework for collaborative open source product integration, and you shouldn't think of it as a closed system. It's not a monolithic take it or leave it software behemoth, but it's a full collection of compatible software capabilities, a vehicle for delivering high quality, reusable software products, and a conduit for future leading edge HPC software targeting scalable next generation computing platforms. It has open source packages. It has liberal licenses like the MIT license. Anybody can download it for free and use it. This is where much of the work goes on at the Performance Research Laboratory at the University of Oregon in Eugene. And I would like to thank the US Department of Energy's Exascale computing project that has enabled the support for both Tau and E4S. And of course, we would like to thank all the collaborators in ECP and the broader computational science communities. So with this, let me just show you a demo of using E4S for running an application. And let me show you how you can use these tools effectively. So I will say Singularity run --nv for NVIDIA GPUs and say ecp.simg. So here I'm now in a container. Okay. And in this container, I can look at Trilinos and use SPAC to compile the code. Here I'm making the build directory. I'm using CMake. Here is a setup script which says load the Trilinos version with CUDA. I can say NVIDIA SMI, and I can see that I have an A100 GPU with 80 gigabytes of high bandwidth memory. And I can say compile.sh, and it will compile the code. And SPAC is in your path. You can see all the packages that it has built. And here you are seeing all these libraries being linked in to the application. These are the libraries, and it's building the code. So I didn't have to build the application, the libraries. Everything is coming from the container. So I can say SPAC find, and it will show me all the packages. SPAC find Trilinos. And this is the Trilinos package. And I can see like SPAC load Trilinos plus CUDA with CUDA arch equals 80. Okay. And here is the build directory. I can say LDD is Zoltan, the binary that it built, and it loaded all these libraries. How many? 37 of these libraries were loaded, including Parmetis, Metis, OpenBlast, Trilinos. And with this, I can run this in this manner. Now it's using MPI in my path, and it's running this code. And it's going through these iterations, and I'm sitting here and I'm wondering, what is it doing? How can I understand what it's executing? So if I run the same code like this, but with tau, I can say tau exec-ebs. Event-based sampling, please interrupt the code execution and then just show me where the application is spending its time. Okay, so here is the execution. Okay, it generates profile files like this. I can even pack them and give it something like Zoltan 1.ppk. And then I can launch the Paraprof browser like this. Sorry. And here is the Paraprof Zoltan 1.ppk, and I can see exactly where it's spending its time. Here is the thread statistics table. It took about 19.9 seconds. 14.6 were in this. I can see the time spent in barrier, reduce. I can even go inside the all reduce and see exactly what it was doing, which libraries were being accessed. Here is the execution of the application outside of MPI, and I can just sort it by exclusive time like this. See, it's using all this time, 12 seconds out of the 14 seconds in this libgomp library. The OpenMP, there's a problem with OpenMP, and here is the libgomp taking up all this time. across the nodes. How much time? Well, it's taking as much as 60% of the time in the OpenMP. And clearly the thread mapping is not going too well in this case. So let me just look at the OMP num threads, and it's not set. So it's just every MPI rank is spawning all the threads. Now, what about this machine? I say LS CPU, it says it has 26 cores per socket, 4 sockets, 104 cores. So I could just say export OMP number of threads to be, say, 26. And then I can run the same code, remove the profile files from before, tau exec-ebs, and run Zoltan again. And here are the profile files. I can say paraprof over here and launch it like, I can say paraprof pack Zoltan 2.ppk. And I can even launch both of them at the same time, like Zoltan star.ppk. And this is Zoltan 2 and Zoltan 1. If I add this thread to the comparison window, this is the total time, say in inclusive 19.9 seconds. And this is the second execution where I can add it. And now I see that the time with the correct OpenMP thread mapping has come down from 19.9 seconds to just 4.4 seconds. And I've been able to shave off a lot of time. It's just 22% of the original execution by learning where exactly it was spending its time. And then I can see exactly what the application is doing and go deep into that and see all the solvers and see exactly where it spends its time, like in this ML exchange candidates or ePetra in the VBR matrix function and so on. So here is the exact line of code in ePetra FEVBR matrix.cpp at line 105, where it's spending 0.75 seconds. So I can just jump right into the code, see the functions and their source line numbers, and then evaluate. You may be wondering whether we can use this framework for AI ML. And here I have, for instance, I can say Singularity run -nv images E4S.simg. Now this is an IC922 system. It's an IBM Power 9 system on which I'm running this. And I just wanted to use an AI ML framework. I may be interested in Python-based frameworks like TensorFlow or PyTorch. And I can say NVIDIA SMI and see that there are Tesla T4 GPUs over here on this IC922 system. You can see uname and it's PPC64LE. And then again, SPAC find in the same way, it has all these packages that are installed. If you prefer module, you also have the module interface where you can say module load tau, for instance. But here, I will show you a Python package. Okay, so if I say Python, I can say import TensorFlow, and then it uses the GPUs, it loads the TensorFlow. I can say TensorFlow test is GPU available. And then it shows me that there are these 3 GPUs, 0, 1, and 2, and the answer is true. So we have many Python packages that are built and say this is an example of using NumPy. And so I can just say Python f1.py, and it's running this code. Here is another code that uses CUDA with PyTorch, and PyTorch is again part of this distribution. So you can just say Python f2.py. You don't have to worry about installing these packages. It's all there in the container. It's accessing the GPU, as you can see. It says Tesla T4 for the Torch device name, and it's running the execution application. And so what I'm trying to get at is that it's getting harder to install all these packages yourself. You may want to just try E4S and use the Singularity container and run the AI ML frameworks or HPC tools directly using a container runtime, or just install it on bare metal. Here is a TensorFlow which uses Keras, and all of these packages are all pretty much in your path. So I can just say Python f3.py, and it will then use the CUDA, and it's using the 3 GPUs, and it's doing this training of this data set. So I just showed you, to recap, how we can use TensorFlow, PyTorch on IBM systems, on IC922, and how you can use x86-64. If you wanted to see how to build this application and run it with a different Intel MPI on this Intel system, I have opt Intel 1 API source here, and I'm using E4S container launch tool, and I can just run this unmodified binary. And by this, I mean I'm loading the Intel runtimes, I'm using the MPI from Intel, and then I'm running the MPI code of the binary that I compiled with the libraries that came from the container. I'm just substituting the MPI using the container launch tool here. And so you can use a different MPI, whether it is OpenMPI or whether it is MVAP-H2 from the Ohio State University, which is an excellent MPI, or MPEG or Intel MPI. So you can run the same application using Intel MPI, and you just have to specify the container to use. So with this, I would like to conclude my talk and say that if you find it hard to install these tools, you're not alone. They are becoming more and more complex, and there is help available. You can measure the time spent in various code regions using Tau. You can do performance evaluation. Tau is included in the Exascale scientific software stack, which includes HPC and AI ML packages optimized for GPUs. You can download everything from this E4S.io webpage. And I hope you find this useful as a software stack. Thank you, and I would be happy to take any questions.
Yes, Samir, we have installed the E4S package as part of Sastra University. As I mentioned in the the message anyway. So
very good to hear that.
Yeah, so we will be using that very well. Thanks for that. Really, you are covering the entire stack. We don't need to worry about getting a lot of packages installed individually. Instead, a ocean, can be placed, and we can start coding. The people can start focusing on coding their applications. Yep. Thank you. Thank you, Samir.
Yeah, thank you, Dr. Samir Shende. It was really an awesome presentation. And it was an insightful talk where, most of us are not aware about Exascale. And I was very particular during the installation that I want that Exascale framework, the entire platform, to be available in my hardware that I'm procuring. And Ganesh has done the installation part of it. I would request you to have an exclusive one-day workshop on Exascale alone, so that it will be an eye-opener for our faculty members. we will have hands-on done for the faculty members, and it will be great if you can give us some time so that we can have that workshop.
Sounds very good. And on our webpage, you will find a workshop that we had conducted, getting started with E4S. And you can just go here and see all our presentations and slides that are available over here. It was a 2-day workshop, and you can learn a lot more about E4S and even, play the videos at 2x speed. So please feel free to look at this, and I would be happy to help you with E4S. And I look forward to other engagements with your team.
Sure. I mean, we'll just take it forward and then just spread about the workshops that you have conducted to our faculty members so that they can go through the content that is already available. And then we may have a kind of query solving session with you if they have got any queries.
Sounds great.
Yeah. Thank you, Dr. Shende. I really appreciate your time and the commitment that you have shown on a Sunday evening. Hope it's Sunday evening as well, right?
Very happy to be here, and thank you for organizing the workshop.
Thank you very much, sir. Thank you. And with this, we come to the conclusion of the first session of today. And we'll break for 15 minutes for a tea break. Tea will be ready outside the auditorium. And we will reassemble by 11:15. And thank you very much all. Thank you.
Thank you. Bye.
Thank you, Samir. Thank you.